Okay, so let's start. Now there are some alternatives to obtaining this expansion. For example, to obtain the expansion of the energy, one thing you can do is, we know that the energy of the nth state would be nothing but psi n h psi n. So let's say h lambda, E n lambda. But we know the expansion of psi n. We said that psi n is n0 plus lambda n1. The first correction plus lambda squared times the second correction, etc. We know what h lambda is, h0 plus lambda h prime. This is exact. And we just write the ket n0 plus lambda n1 plus lambda squared n2 plus etc. So assuming you know the corrections to the wave functions, you can also just use this relation. So this tells you that En0 is equal to N0 H0 N0. This is already, we know that N0 is an eigenstate of H0. En1, the first correction, would be, just collect the lambda to the 1 terms on both sides. So we have lambda to the 1 will be, let's see, N1 H0 N0 plus N0 H prime N0 plus N0 H0 N1. But now H0 acting on N0 is an eigenstate, so it will just give me an E0 times overlap of N0 and N1. But the overlap of N0 with any of the corrections, we impose that boundary condition that should be 0. So this is 0, and so this will be 0. Those two terms are 0, and you are left with our previous result. And you can just take the lambda squared terms on both sides, and you still get the same correction. You can do a similar expansion rather than just matching the terms of the same powers of lambda on both sides. Another trick that you can do is just this one. So this is the equation that we would like to solve. And let's put the lambda. And we know that h lambda is h0 plus lambda h prime. This is En0 plus, let's say, delta En. Or let's not do this. En n, or E0 minus En n should be equal to lambda times h prime n. Or we can say that n should be equal to N0. Well, this equation over here that we write, you can just think of this as an inhomogeneous differential equation. So the solution of this one will be the solution of the homogeneous equation plus the solution of the particular solution, plus 1 over H0 minus En times lambda, let's say, H prime n. Now that operator over here, 1 over the operator, is just the inverse of our operator. So what you can do is you can just try an iterative solution. So n should satisfy this equation. You can just take this expression and use it over here. So n should also be this solution. Should also satisfy this equation, plus lambda 1 over h0 minus en h prime n0 plus lambda squared 1 over h0 minus en h prime 1 over h0 minus en. You can repeat this. You can just take, if you like, either put all this expression over here, or you can just take all this expression and put it over there. So this is the lambda to the 0 term. This is lambda to the first correction. This is the correction proportional to lambda squared, etc. So you can also calculate it like this. Now, of course, you have to make sense of this term. What does this term mean? But you can just use a complete set of the eigenstates of H0. Let's say 1 over H0 minus En, H prime n 0. This will be equal to sum over all m0, m0, 1 over h0 minus en, h prime n0. Well, h0 operator, this is just a number. This operator I can also act over here, so that will give me em0. This is almost like the previous expression. Not exactly though. You see here it appears En, not En0. Okay, I made a mistake over here. You see, I have to separate this En to En0 plus the correction. Now the reason is this is not the solution of this equation, this homogeneous equation, unless I make that separation. So let me just correct it. This is En0. But of course, on the other side, I also have delta E. Delta En is also of the order of lambda, the first correction. So you can just keep track of those corrections. Now this is exact. Now, because En0 overlap with, well, the corrections, their overlap with N0 is just 0, the zeroth states. So this should be exact. So this is just an alternative way of obtaining the expansion. Now, of course, up to now we have been assuming that there is no degeneracy. Well, the problem is what to do if there is a degeneracy. You already know systems which has a degeneracy. For example, the hydrogen atom. In the hydrogen atom, you do have the degeneracy of, for a given n, all possible values of L have the same energy. So this treatment over here, we cannot really apply. We have a degenerate system. Well, here I had made a mistake that I have to separate this En also as En0 plus the correction here. Now let's see what we are actually doing. So we had defined this H lambda with some small perturbation that we call H prime. And we had written that our states will be our unperturbed states plus lambda N1 plus lambda squared, the second correction, etc. So these are the corrections for our energy eigenstates. So you can just imagine that we have this knob which controls lambda. If we set lambda to 0, we are in the unperturbed solutions. We turn on the lambda slightly. If lambda is very small, we are still very close to the unperturbed solution, our energy eigenstates. We turn it on, we are slightly modifying it as we increase the value of lambda. We are perturbing it more and more, and eventually we reach the value lambda. Whenever we turn off lambda equal lambda to 0, we recover our unperturbed eigenstates. When we turn on lambda, we recover the perturbed eigenstates. Now, when there is degeneracy, the problem is we don't have a unique choice of energy eigenstates. So you see, let's just assume that N0 and let's say N prime 0 are degenerate. That they have the same energy. But then, in fact, we have an infinitely many states that have the same energy. So assuming we find the solution of the perturbed system, so the question is, when we turn off this lambda, when we turn off this perturbation, which state does that go to? We don't really know a priori. So we have our eigenstates of H lambda. As we set lambda go to 0, it goes to an eigenstate of H0, but which one? Because there is more than one. So that's the main cause of problem in the degenerate perturbation theory. We don't know which one it goes to. So we will make an assumption. In the previous one, in the non-degenerate case, there was this single state, and we knew that this perturbed state, when we turn off lambda, it goes into this unperturbed state. But in this new case, in the degenerate case, we don't really know what the state is. It can be this one, or any combination of those two. So that is the thing we have to take into account. Now what we will do is we will just write N. Let's say I don't know if it is the N0 state or N prime 0 state. We don't know. We have to determine these alphas and betas. Plus, of course, there will be corrections of the order of lambda. Higher order corrections. For the energy of this state, it will be, just as in the previous case, En0 plus, let's say, the first correction, En1. And what else we know? We know that H0, N0, this should be En0, N0, and H0, N prime 0, is equal to En0, N prime 0. This is what we mean by degeneracy. Now let's try to repeat what we had done before. H0 plus lambda H prime acting on alpha N0 plus beta N prime 0 plus terms of the order of lambda. This should be equal to En0 plus lambda En1 plus terms of the order of lambda squared multiplied with alpha n 0 plus beta n prime 0. Now let me just do one more. Write this state. Plus lambda, the first correction, plus order of the lambda squared. Now, if you just look at the lambda to the 0 terms, that just gives us the unperturbed Schrödinger equation whose solution we already know. So let's look at the first corrections, the lambda to the 1 terms on both sides. Now, on the left-hand side, we have H0 and 1 plus H prime alpha n 0 plus beta n prime 0. This is the left-hand side. Now, on the right-hand side, we have En 0 and 1 plus En1 alpha n 0 plus beta n prime 0. Now again we do the same trick. We multiply both sides by the unperturbed nth eigenstate ket bra. The first term on the first line and the first term on the second line, they just cancel each other. Oh, by the way, yes, they cancel each other. And so what is left is alpha n 0, h prime n 0, plus beta n 0, h prime n prime 0. This should be equal to En1 times alpha. Now we are assuming that although they are degenerate, we are choosing a basis that is orthonormal. So n0 is orthogonal to n prime 0. Now this is one equation we obtained. Well, since we have already two unknowns, that means alpha and beta, we need one more equation. But we can also multiply by n prime 0. Okay. So, because you see the trick that allows us to cancel these ones is that we have to multiply by a bra such that when H0 acting on that bra, it gives me E0. And I have two such states. I can use both of them, and both of them will give me a different equation. Now, if I multiply by n prime, what I obtain will be alpha n prime 0, h prime n 0, plus beta n prime 0, h prime n prime 0. This should be equal to En1 times beta. So I have two equations for alpha and beta, and also En1. Well, in general, that is not such a nice thing to have, because we have three equations and three unknowns and two equations. But let's just rewrite this. You say this is not a homogeneous, this is a homogeneous equation. So these two. So not all the time they have a solution for a possible solution for En1. Now let's write this in this form. N0, H prime N0, N0, H prime N prime 0, N prime 0, H prime N0, N prime 0, H prime N prime 0, this 2 by 2 matrix, multiply with alpha and beta, this is equal to En1 alpha and beta. So this matrix equation is in fact corresponds to these two equations over here. Well, the general solution for an arbitrary value of En1 of this equation is that alpha is equal to 0, beta is equal to 0. But that's not the solution we want. So we want a non-trivial solution, which is non-zero. So the non-trivial solution exists. Only if determinant of, let's say, h prime and n, h prime and n prime, h prime n prime n, h prime n prime n prime minus En1 times 1, 1, 0, 0. This should be equal to 0. Only if this condition is satisfied, then we have a non-zero values, possible values of alpha and beta. Now, furthermore, we also have one more condition. We would rather have a normalized state when we turn off the interaction. So alpha squared plus beta squared should be 1. So that kind of uniquely tells us, well, this equation already tells me what En1 is. So we had started with two degenerate solutions. Basically, what this tells me that En1 has two possible values. One will be the value of one of the, when we turn on the interaction, what happens is the degeneracy will just disappear. So they will have received different states will receive different corrections to their energies. So they will not have the same energy anymore.
But
so
you assume them together, right? As a single correction.
Well,
N1.
now you see, now we have two states.
Right. They receive different corrections, but we add them and say it's N1.
No.
I see. Okay.
En1 has two different possible values. So let's solve this. So we have the determinant h and n prime minus En1, h and n prime, h prime n prime n, h prime n prime minus En1. This is equal to h and n prime minus En1, h n prime minus En1.
Two solutions.
It has two solutions. So let's say En1 is either A plus B or En1 will be equal to A minus B. Now we have two solutions.
I mean the correction term for the
Wave function. No.
wave function. Yeah.
Let's do an example.
Okay.
That will be much more clear. Let's assume we have a simple system which the Hamilton H0 itself is a matrix. Let's say epsilon, epsilon, 0, 0. Let's add some perturbation to this one. Now this is we can also solve it exactly. Let's say the perturbation is 0, 0, delta, delta. They have to be Hermitian. So this is our perturbation. Now H is epsilon, delta, delta, epsilon. If you diagonalize these, we already know what the eigenvalues and the eigenfunctions are. H acting on 1, 1. Let's normalize it properly. This is epsilon plus delta. 1 over square root of 2, 1 over square root of 2. And h 1 over square root of 2 and minus 1 over square root of 2. This will be epsilon minus delta. So what happened is, before we had the eigenstates, we had chosen the eigenstates as 1, 0 and 0, 1. These were our eigenstates. Then when we turned on the interaction, we saw that the eigenstates are no longer these ones. They're just the linear combinations of these ones. And each one of these new eigenstates have a different energy. Before they had the same energy, and now they have different energies. Now let's just do the perturbation expansion over here. Okay, so let's say this is our one state. Let's define this as our one prime state. So to determine the energy, correction to the energy, what we do is we just kind of form the matrix representation of H prime in this degenerate subspace. So in the simple problem, the degenerate subspace is all of our Hilbert space. But in a general problem, your degenerate subspace could be just a smaller subset of the Hilbert space. And so we have to form H prime 1, 1 prime, now H prime 1, 1, H prime 1, 1 prime, H prime 1 prime 1, and H prime 1 prime 1 prime. We have to form this matrix. Now if you form this matrix, this is nothing but 0, delta, delta, 0. Now we have to determine alpha and beta. Now to determine alpha and beta, first we have to determine the correction to the energy. And the correction to the energy, remember we have this matrix. We subtract the first correction to the energy, this one, multiplied by the identity matrix. So to determine the energy, to determine En1, we solve the determinant of minus En1, minus En1, delta, delta. This is equal to En1 squared minus delta squared. No. This should be equal to 0. So now we know the eigenvalues. The possible first order correction. This is either equal to delta or En1 is equal to minus delta. Now let's determine alpha and beta. Once we determine the eigenvalues, now alpha and beta should satisfy this one. 0, delta, delta, 0. Let's look at the equation. Here we had constructed the matrix of H prime in our degenerate subspace. When this matrix acts on alpha and beta, this is also a representation of our wave function. It should give me my eigenvalue times alpha and beta. So I have to find two solutions, alpha and beta. This should be equal to plus or minus delta alpha and beta. I have to solve these equations. One for plus sign, one for the minus sign. Well, just so that we can solve both of them together, let me put a plus and minus over here. Either take all the lower signs, so you get the solution for the plus delta eigenvalue, or take always the upper signs, you get the solution for the minus delta eigenvalue. Now if you multiply, so we have beta plus minus times delta, alpha plus minus times delta. This is equal to plus minus delta alpha plus minus delta alpha. Yes. Plus minus. No, the lower side is beta. So what we have is beta plus minus delta is equal to plus or minus delta alpha plus or minus. So I can just cancel the deltas. So beta plus or minus should be equal to plus or minus alpha plus or minus. So this tells me that beta plus is equal to alpha plus, and beta minus, I take the upper signs everywhere, beta minus is minus alpha minus. If I also properly normalize them, corresponding to plus delta, I have the state alpha plus beta plus, which is 1 over square root of 2 and 1 over square root of 2. And for minus delta, I have the state alpha minus beta minus, which is 1 over square root of 2 minus 1 over square root of 2. So what this basically tells me that if I have a degenerate state, first I have to diagonalize H prime. And once I diagonalize the H prime, the states that contain H prime, that diagonalize H prime are the states that I should use in order to do the perturbation expansion. The rest is identical to non-degenerate perturbation theory, because you see the problem over here in the non-degenerate case, let's look at the En1, psi n1. Now the problem here was that I might have different states having the same energy. Now what I did was, if I have this degenerate case, I diagonalized H prime in that degenerate subspace, so that H prime no longer couples the matrix element of H prime between two different degenerate states is now 0. So effectively what I did was I chose my 0th order states such that H prime, the matrix element of H prime, is 0 between degenerate states. Since it is 0 between degenerate states, those terms do not contribute anymore, and there's no problem in using this expression. I'm safe. That expression becomes a safe expression. That is the main trick. So degeneracy kind of gave us a freedom to choose our basis, because if you have two states having the same energy eigenvalue, any superposition will have the same eigenvalue. So somehow we have to choose one combination or choose some other combination. Now we use this freedom to choose our states such that H prime doesn't, the matrix element of H prime between degenerate states is 0. And then they don't contribute to this sum, and hence there is no problem with having 0 denominator. Any questions on this one? So do you know any degenerate systems? Now the hydrogen atom we will study next week. Any other degenerate systems? Well, you see, in this one also, if you remember, if we just reinsert our del lambda, initially both of the states have energy epsilon. So they both start from here, both states. As we turn on lambda, one of them increases linearly. The other one just decreases linearly. This is epsilon minus delta. This is epsilon plus delta. So in this sense, this perturbation lifts what we say that the degeneracy is lifted by this perturbation. So now here we have two states having the same energy, but the change in the energy as we change lambda is different. So although they coincide when lambda is equal to 0, they differ when lambda is different from 0. Now let's look at another example. Like the previous case, H prime is again 0, delta, delta 0. But let's take H0 to be epsilon 1 and epsilon 2. Different energies. So this is the non-degenerate case. Let's say this is the first state. H0 acting on first state is epsilon 1, unperturbed first state. And H0 acting on unperturbed second state is epsilon 2 times the second state. Now let's look at the correction to the energy of the first state. The first correction. Well, it will be just the first state, unperturbed first state, H prime, unperturbed first state. The first order correction is we know what H prime is. First order correction is just 0. Now 1 is 1, 0. 2 is 0, 1. This is 0. There is no first order correction. The first order correction to the second state this is also 0. Now let's look at the second correction to the energy.
First order, second order to second order.
No, okay, first order, sorry. First order correction to the energy of the second state. They are both 0. There is no first order correction to the energies. Let's look at the wave function first. The correction, first order correction to the first state. Now let's see what was our expression. This is what we had for the first order correction. Well, since we are summing over all the other states, in fact here we have just a single other state, so the first order correction is just unique. So K should be 2, 2, 0, H prime, 1, 0, 2, 0, divided by E, and 0 is epsilon 1 minus epsilon 2. This is equal to, well, that matrix element of H prime is just delta over epsilon 1 minus epsilon 2, 2, 0. We can write the correction to the second state, the first order correction to the second state. This will be 1, 0, H prime, 2, 0, 1, 0, divided by epsilon 2 minus epsilon 1. Again, this matrix element is again delta. This is just delta over epsilon 2 minus epsilon 1, 1, 0. So upside the first state is 1, 0 plus delta over epsilon 1 minus epsilon 2, 2, 0, plus higher order corrections. And the second state will be just 2, 0 plus, or let's say minus, delta over epsilon 1 minus epsilon 2, 1, 0, plus the higher order corrections. Let's look at the second order correction to the energy. Now, because we will, after this, we can actually solve this problem exactly and see if our perturbation expansion and the exact results match or not. So this was the correction to our energy. The second order correction to the energy of the first state, again, there's just one term in this expansion, minus 2, 0, h prime 1, 0 squared divided by epsilon 1 minus epsilon 2. This is equal to delta squared over epsilon 2 minus epsilon 1. And the second correction to the energy of the second state, 1, 0, h prime 2, 0 squared divided by epsilon 2 minus epsilon 1. This is minus delta squared over epsilon 2 minus epsilon 1. Now let's look at the exact solution for the energy. Now remember our Hamiltonian is this one, epsilon 1, epsilon 2, delta, delta. And the eigenvalues of this one you can determine by determinant of h minus epsilon 1. This should be equal to 0. And this determinant is epsilon 1 minus epsilon, epsilon 2 minus epsilon, minus delta squared. This is equal to 0. So already from this expression, you see that all epsilon depends only on delta squared. It doesn't depend on delta. So there's no correction. There are no corrections to the energy that are to an odd power of delta. You see, here, the epsilon, the energy eigenvalues are determined by this equation. But this equation doesn't depend on delta. It depends on delta squared. So if you make an expansion in terms of delta, delta will never appear. Only delta squared will appear. Let's see. Epsilon squared minus epsilon 1 plus epsilon 2 plus epsilon 1, epsilon 2 minus delta squared. This is equal to 0. Epsilon. So epsilon is equal to epsilon 1 plus epsilon 2 plus or minus square root of epsilon 1 plus epsilon 2 squared minus 4 epsilon 1 epsilon 2 minus delta squared divided by 2. This is equal to epsilon 1 plus epsilon 2 plus or minus epsilon 1 minus epsilon 2 in absolute value square root of 1 plus 4 delta squared divided by epsilon 1 minus epsilon 2. Now, there are a couple of things we can already say by looking at this expression. We already know beforehand that our expansion of the states and also of the energies, they always go with delta over epsilon 1 minus epsilon 2. So if epsilon 1 minus epsilon 2 is smaller than delta, then delta over epsilon 1 minus epsilon 2 is a large number. So we cannot just keep as one term and say that this is our approximate solution. Just having delta small doesn't guarantee the convergence of our perturbative expansion. It's not delta, it is delta over epsilon 1 minus epsilon 2 that determines whether our expansion converges or not. So also here, it's also apparent. Now, you can, if you take that square root, you can expand it, that square root, in powers of delta, only if delta squared over epsilon 1 minus epsilon 2, sorry, here I have a square. Only if delta over epsilon 1 minus epsilon 2 is much, much smaller than 0. Only in that case, I can Taylor expand that square root. Otherwise, I cannot. Or I can, but the expansion will not converge. So I cannot do that. Now we can already judge it from the expansion. Now this is a case where we know the exact solution, so we can just look at the exact solution and just obtain the perturbative expansion. In general, we will not know the exact solution. So we are just direct. The only thing we have is the approximate solution, and arguments like this, whether that correction is small or not, that can tell you whether it will converge or not. Not exactly, but at least it will. You can make an argument that it might converge. Because we have series like the sum of 1 over n, all the terms get smaller and smaller as you increase n, but it diverges. Now, of course, this was the energy eigenvalues. You can do the similar. Once you know the exact energies, you can solve for the energy eigenvalues and see if this is a solution or not. Let's do one trick. Do we have time? Yes. I will take 5 more minutes. So we know already that the energy eigenvalue should be orthogonal, and they should be. We should be able to write them in terms of our unperturbed states. So if you have just 2 states, and any state it has to be normalized. So the pure solutions, exact solutions, should be written in this form. Well, in the first term, I could have just left the coefficients as arbitrary, but I know that the square of those coefficients already give me 1. If you like, you can just add some phase, but I can just redefine my 0th order solution so that that phase also doesn't appear. So these are my exact solutions. The only thing I need is that their overlap is 0. So I need the only thing left is what is theta? The easiest way to find theta is to use that this should be equal to 0. Why? Because H acting on 1 will give you some energy eigenvalue times the first state. Energy eigenvalue, I can just take it out of the matrix element, and what remains is that the overlap of 1 and 2. But they have to be orthogonal to each other. But this equation tells me
Does it give another condition on theta?
Yes. This equation gives a condition on theta, using which I can solve for theta. Let's see, minus sine theta, epsilon 1, sine theta, cosine theta, epsilon 1, plus sine theta, cosine theta, epsilon 2, minus sine squared theta delta plus cosine squared theta delta. This should be 0. Well, let's use some trigonometry. Cosine squared theta minus sine squared theta is cosine 2 theta. So the first term is sine theta cosine theta times epsilon 2 minus epsilon 1 plus cosine squared theta minus sine squared theta times delta, this should be 0. Epsilon 2, or let's see, 1 over 2 sine 2 theta times epsilon 2 minus epsilon 1 plus cosine 2 theta delta should be equal to 0. Or tangent 2 theta should be equal to 2 delta divided by epsilon 1 epsilon 1 minus epsilon 2. Well, let's just make the assumption that theta is small. That the delta is much less than epsilon 1 minus epsilon 2. Then tangent 2 theta is approximately 2 theta. So that tells me that theta is equal to delta over epsilon 1 minus epsilon 2. So this is my theta. Now let's look at my corrections. Yes, here are my corrections. Let's see. Remember, theta is delta over epsilon 1 minus epsilon 2. Since theta is small, cosine theta is almost 1, sine theta is minus 1. Sine theta is theta. Let's see, cosine theta is 1, sine theta is just theta. And it gives me delta over epsilon 1 minus epsilon 2. I might have made a sign mistake somewhere, right? No. Yes. So this is fine. The second one is sine theta is minus delta over epsilon 1 over epsilon 2, 1. Cosine theta is almost 1. Well, there is one thing though. In our perturbative expansion, we made an assumption that the zeroth order term has zero overlap with the higher order terms, with the corrections. That's the condition we imposed. So that means that all the corrections that will come to my states are, to the first state, will be proportional to the second unperturbed state. I won't have any correction proportional to the first unperturbed first state. But you see, I have if you look at this one, the first state eventually gets corrections that are proportional to the first unperturbed state. So what's going on? So here, there won't be any correction to 1, 0. All the corrections will be proportional to the 2, 0 state. No correction will be proportional to the 1, 0 because that's our boundary condition that we are imposing on the corrections. But here we do get corrections to the 0th order state. Corrections proportional to the 0th order state. Okay, that is homework for you. So did you understand the question? In our perturbative expansion, we impose the condition on the corrections that they should have zero overlap with the zero order term. In this case, we have just two states. So if the zero order term is the 1, 0 state, all the corrections should have zero overlap with that one. That's our boundary condition in our perturbative expansion. But that means that all the corrections will be proportional to 2, 0. I don't have any correction proportional to 1, 0. The 1, 0 term will stay there, its coefficient will stay to be 1. Not cosine theta. Yes, normalization. In perturbation, we are not imposing the normalization. Here we have the normalized state. So that term over here that delta and this delta over here, they are in fact not the sine of theta. They are the tangent of delta. Because if you just take out this cosine theta, 1, 0 plus tangent theta 2, 0. If you take the cosine theta, you have 2, 0 minus tangent of 1, 0. And that's also something you can check. Just calculate the second order correction to these ones, to the states we have. If you calculate them, you will see that you get the next term in the expansion of tangent delta, tangent theta. Yes, any questions? Don't forget to fill the doodle. And there are only 3 students for the time being. 4, okay, that makes 4. There are still 3 left. Okay, on Monday I would like to finalize the other hour, whether it will be on Saturday or some weekday or not.